Hey, this is Warren Redlick. This is my conversation with James Douma about Tesla full self-driving. In this part of the video, we talk about object identification and we talk about measuring how FSD is doing. You can think about subjective measurement of how it's doing, how I feel about how it's doing versus how you feel about how it's doing, and objective measurements. What kind of objective things are there that we can look at or that Tesla can look at to see how is it doing? Are you ready? Let's go. So one of the things that I think is a really important feature of what's going on is object identification. The pixels come in and the car is trying to identify objects. So it sees a stop sign, it sees a traffic light, it sees a pedestrian. Do you think they build up a vocabulary for the software to understand what objects are?
The data they use for training, it's in the business, we call it the training corpus, right? It's this set of data that you're going to use. It will include explicit examples of things that you think are important to identify explicitly. And it will include groups of things that you think are significant in some way, but which you don't necessarily need to explicitly identify. So for instance, a stop sign you want to explicitly identify, and you may want to categorize it. In fact, he's talked at length about stop signs, right?
Stop sign on an arm.
A lot of different kinds of stop signs in the world.
Right.
And they're super context. The stop sign on the school bus is a stop sign.
Yes.
And then there's, stop signs on, some gates that go up and down or gates that open. And so you have all these state dependent stop signs.
Did you see recently there was a stop sign on a billboard and the Tesla stopped because there was a billboard off to the side of the road that had a big stop sign on it? Yep. And it got confused because it saw a stop sign that wasn't really a stop sign.
It's a context-dependent thing, right? Yeah. I remember when the stop sign detection at first happened, and if you saw a school bus with a stop sign on it, it was a problem, right? I mean, so we'll just take the stop sign, the stop sign on the school bus thing. Okay, so my neural network has been told to identify bus, right? Maybe it doesn't have a category for school bus yet. And it's been taught to identify stop signs. So at some point, do I want to create a special category for, stop sign on a bus? So you could imagine that there are different ways to go at this problem. Like you could have a human being say, oh, is there, here's a stop sign, here's a bus. And the human written code, is this a stop sign on a bus? And then deal with it that way. Or you could say, I'm going to collect a corpus of stop sign on a school bus things, and I'm going to recognize that as a separate category, and I'm going to deal with it that way, right? So those are both legitimate approaches, and depending on the accuracy and how difficult you think it is to write this piece of code, how buggy it will be, how hard it is to integrate it, you might choose one path or the other. In fact, looking at Tesla's evolution, it's frequently been the case that they have handwritten a solution to something that they needed to solve to do what they want to do today. And then later, more and more of it gets absorbed by the neural network. So maybe initially you've got the stop sign and the school bus, and you already have the school bus thing working in your neural network, and you already have the stop sign thing working. And so initially, human writes is this a stop sign on a school bus thing? And what do I do if it is? Sort of thing. And then a little farther down the road, your engineers might say, this piece of code, it's not working so great. What we really need is a stop sign on the school bus category that the neural network detects directly and tells us. So then they go, okay, we need a bunch of pictures of school buses that have stop signs on them. So then you build you take a bunch of pictures of school bus stop signs. You can create a latent representation of this, which is just, it's basically this mathematical representation of what is happening at a particular stage in the neural network, which is very strongly correlates with when the neural network is seeing a stop sign on a bus. You push that out to the fleet and you say, you can tell every single car out there in the fleet, all those millions of cars, you see one of these, take a snapshot, send it to me, right? And 10 days later, they've got 100,000 pictures. So they have some people go through those, say this one's good, that one's bad. You stick those in the training corpus and you say, hey, when you see this, give me the stop sign on the school bus flag, and blam, you've just added a thing. In 10 days, you can go from an engineer deciding we need this in order to improve the performance, to go out to the fleet, get the data, add it to the training corpus, turn the crank on, this is Carpathy's data engine, right? And now your neural network is telling you with some significant level of accuracy, when that phenomenon is occurring in the world, when I have a stop. And you could go further. You could say stopped school bus with the stop sign extended, or is the stop sign extended or not? So now you have a state variable. And over time, what happens is you see the neural networks, they accumulate more and more of these variables, right? And then occasionally you see a thing where they consolidate a bunch of them down into a single variable that they want, which better captures the overall situation. And then you see the neural networks change and they get rid of all those ones they had before, right?
Yeah.
So things expand, they add more variables, then you get consolidation, and then they expand again. But the general trend is that you see more neural networks and they get bigger and there are more outputs.
So we talked about object identification and probability vectors a little bit, that, you know, it's trying to figure out where something might go, or hopefully that it's not, if it's a stop sign, it's not moving. How do you measure how well it's doing? And I think there are objective things you can look for and there are subjective things that you can look for. So in my mind, an intervention, when a human hits the brakes, that's the human saying the car did something wrong, but the human could be wrong, right? The human steers, the human might not have seen something the car sees. It's the human's and like, you might have hit the brake, but I might not have hit the brake because we have different reactions to what we see on the road. You and I might drive differently from each other. So there's a subjectivity to human input. Objective input would be something like what Andre Karpathy described in the Robot Brain podcast, flicker. It sees a stop sign, and then the next frame, it thinks it's not a stop sign. It thinks it's a yield sign. And then it flickers again, and it thinks it's a stop sign, and then yield sign, and finally it settles on stop sign. So that's an objective sign it's not identifying well, right? Or it could identify that object better. Another objective sign would be, I predicted that thing wouldn't move, and it moved. Or I predicted that thing would move with this probability vector, and it moved to a spot that was either completely outside of where I predicted it would move, or to it was a low probability move. So those are two examples of things that I think are things you can objectively measure how well it's doing. Do those make sense as things that you could objectively measure and then say, gee, we had a lot less flicker in this drive. And things moved within the vector that we anticipated. So it seems to be doing better. If we're seeing a lot of flicker, if we're seeing objects not moving where we predicted, then we're seeing it worse. Does that seem like some pretty good measures Tesla could be using to evaluate how well is this version of FSD working?
Yeah, sure. I mean, it's nice when the neural network is not just telling you what it's seeing, but it's also telling you the confidence with which it thinks it's seeing stuff. And of course, ideal in the best of all possible worlds, everything it tells you with high confidence, and that confidence is well placed. You know, when you go back and you test it, when you test the neural network, so they'll do regression tests on these neural networks. You know, they got this whole giant suite of canned phenomena that they want to test, and they know what the results should be. So they train a neural network, they regression test it against all these canned scenarios that they have. And if the network is giving them higher confidence of the correct answer, right, then you're getting closer to the world that you want. But of course, this not just doing regression tests on your canned capture.
Just real quick, I think for the audience, I know what a regression test is, but could you explain to the audience what a regression test is?
A regression test, when you're building a piece of software and you want a particular output, one of the things that you can do is you can say, well, I know for this set of circumstances, I should get these outputs. In the future, if you change that code, you still want to get the answers that you got on the previous code. So you have this library of tests, which are where you know what the right answer is for the test. So when you make a modification to the code just to check, make sure you haven't broken anything, you run the code against all these tests that you have in the can. Those are called regression tests.
By regression test, you don't mean statistical regression. You mean you're making sure it's not regressing. It's doing stuff as well as it did before, and it's not getting worse on the things that it already did well. Well, I guess I was trying to figure out, what else do you think they measure besides object identification, accuracy and consistency, and probability vector predictions? What are some other big things that might be objectively measured?
What might not? Yeah, that's a very large space of.
No, but what would be important for them to measure to see how well is it performing?
It's a stack of functionality, right? At the end of the day, what you want is you want the user to get in the car, tell it to go from A to B, and for it to get there, and for there to be no interventions, and also not trip a lot of other flags. You don't want any. If the car ever had to brake hard, you want to evaluate, well, did it have to brake hard because it made a poor judgment or did it have to brake hard because of some unforeseeable phenomena? Or, is the steering wheel wobbling back and forth, left and right? And then if you see a lot of variance in the output of things, like it's accelerating, decelerating, as opposed to holding, you want to try to understand what's stimulating that behavior, right? And if it was appropriate or not. I mean, if you see the steering wheel regularly wobbling a lot on a lot of different cars, it's probably not because the circumstance is dictating it. It's probably because there's something wrong in the algorithm, right? So there are any number of sort of little heuristic rules that you could come up with where you observe the cars in the real world and you use that as an evaluation criteria to help you decide if at the top level the software is working well. But of course, as you come down the stack, there are lots of small things also. One of the things that the neural network makes a determination of when you approach an intersection, if you live in a big city, it's pretty common to come to an intersection where you have a bunch of different lights, and the lights are relevant to different drivers. There's a left turn light, maybe there's a right turn light. There might be different lights for different lanes. So the neural network has to figure out which of those lights is the light that applies to you. You come to the intersection, it sees 3 traffic lights, and it needs to understand which one of those is the one that's relevant to you. Say you're the engineer who's tasked with getting this function to work really well, right? And you're not sure how well it's working in the world, and you've already gone through shadow mode, and because the first thing that you do is you write this function, you push it out in shadow mode, and then you might have some tests on the vehicle behavior that you would look. For instance, when it's sitting in shadow mode and it comes up to an intersection, you might go through this phase where you say, if shadow mode predicted that this was the light that was relevant to me, and the light was red, but the driver drove through the intersection, I might be wrong, and I might want to look at those. So let's capture all those events so that we can take a look at them, right? So you might go through that phase. Then later on, when it gets good enough, maybe now you're controlling the car, maybe you're not controlling the car. But you can write a heuristic to evaluate how well that particular aspect of this function is doing. For instance, did I come up to an intersection, see the light that was relevant for me, see that it was green, decide to grow, and then the driver had a panic stop, right? Because that might be a sign that I was wrong, and I need to look at that. So I can bet you that particular rule I just described, that's in the system, right? Because those are events they definitely want to catch.
Yeah.
So there will be a whole laundry list of those kinds of things in the system, which are, I kind of describe them as a code harness right now. You've got this horse, you're riding it, and you mostly trust it, right? But you don't completely give up controls. You have some framework that you let it operate inside of. And especially when you're not, for aspects of its behavior that you're not certain about, you keep a pretty tight rein on the range of things that you allow it to do to prevent a catastrophic outcome. And then as your confidence grows and it's demonstrated that it can handle a wider range of circumstances with better and better outcomes, then you can gradually loosen up those blinders that you've put on the thing. So when you ask me, well, like, what's a good candidate for that? Like, I could probably all day long, we could stand here, we could come up with, oh yeah, if autopilot decided to do this and then it saw this other behavior, that's a sign something could be wrong. And you capture those events. So there are lots of different kinds of triggers that you can have. But the one that Andre described, where essentially you see a stop sign, then you don't. You see one that you don't. Well, we know in the real world that stop signs are persistent. Right?
Yes.
They don't exist and not exist and not. So we're taking a human intuition that generally, if you see a stop sign, you should keep seeing it until you pass it. We're taking that human intuition and we're writing a rule and we're applying that filter to what the vehicle is reporting back to us to understand, does it make sense given our human understanding of how this phenomena should be in the world? And there's just a vast number of those that you could write, and there are probably a very large number of those rules operating in the car in all the cars right now.
Is getting the traffic light wrong really just a subset of object identification? Or it's, no, I knew it was a traffic light, I just didn't know which one was important. So it's sort of like, when I talked about object identification and sort of like a library of objects and then probability vectors, I guess another thing that we want the car to do is like assign attributes to objects, right? So, and you see a traffic light, maybe it's not I'm identifying a red light, I'm identifying a green light, I'm identifying a traffic light, and I'm identifying an attribute. It's green, it's yellow, it's red, it's flashing.
Mhm.
And there may be other attributes of objects that I haven't really thought through.
Yeah. This is where the long tail of the world comes in, right?
Yeah.
Like you and I can sit here and we can talk and forever. Tesla's engineers can sit in a room and they can talk forever about this kind of stuff. And what happens is you're going to build a piece of code, you're going to put it out in the world, and it's going to find all kinds of things that you never didn't think about, right? So the right way to solve this problem is not for a bunch of smart people to just rack their brains trying to come up with every possible thing that could go wrong. You build something that's constrained in how it operates, you push it out into the world, and you look at where it fails. And then you take that information, you refine it, you push it out again, and you just keep doing that. And the thing is, the world is so perverse that you are never going to get to the end of the extraordinary situation. It's sinkholes.
Yeah.
I mean, who's driving down the road? Or have you seen that footage of those people who are like driving in coastal Japan when the tsunami came in? Like, oh, tsunami! I'm going to turn around and go uphill from here. Right?
Tidal wave.
There are things that you're just not going to see, and they're super common things that are also, things fall off of trucks. But what can fall off a truck? Anything can fall off a truck, right? I mean, something you've never seen. I drive down the road and see things on the back of flatbed trucks. I got no idea. Like, I'm an engineer. I think about machines all day long. I see metal contraptions on the back of trucks. I have no idea what those are. Or like, how am I going to train a neural network to recognize those individually? You have to treat them as a category, right? At some point, you're like, something, you have a category, which is stuff falling off of trucks, right? And it has to be able to recognize anything falling off a truck, right? And sort of understand that I probably want to avoid that thing that fell off the truck.
Human falling off truck might be more significant than squirrel falls off truck.
Or human falling off of motorcycle, human falling off of bicycle,
So,
old lady falling down in crosswalk,
Tesla has to be measuring how well it's performing internally. And it's not just, like, I don't think interventions is really the dominant measure. Well, let me ask you the question this way.
It's not going to be numerically dominant. They probably get 1,000 other trivial, notifications for every human intervention they get.
Right. So, well, I mean, one of my thoughts is that at some point it becomes better than human. And then the odds...
It's already better than human in lots of ways, right?
So when it's better...
It doesn't get drunk. It doesn't get tired. It doesn't adjust the radio. It's not yelling at its kids. It's, it's not fixated on the blonde and the, 2 lanes over. I mean, there's all kinds of failure modes it just doesn't have.
No, but what I meant was, where I was heading with that is, there's going to come a time when the human decides to intervene because he didn't see something the car saw. And the car, in other words, the car wouldn't go at an intersection because it saw something coming. And the human's like, why are we waiting? Hits the gas. And the car's like, nah, we're not going. But that's an intervention that would go back to the home office, dojo, whatever, to like evaluate, okay, what do we have to do here? At some point, the interventions become more likely incorrect. Like right now, an intervention is probably 75 to 90%. The car probably did something wrong. Somewhere down the road, an intervention is going to be like 10% chance the car did something wrong, 90% chance the human is wrong. And then at some point, it's like 99% chance the human's wrong. Because Elon has this saying that you want to get to the point where all input is error.
I wouldn't be surprised if autopilot is already in a zone where most human interventions are unnecessary. So speaking of the human intervention thing, the worst Waymo accident ever, where the Waymo vehicle is coming to an intersection and it starts slowing down. And the driver looks at the situation and he doesn't see a good reason for it to slow down. So he overrides the car and goes. Well, Waymo saw a FedEx truck running the light, right? And the human driver didn't see it. The Waymo vehicle tried to stop. The human overrode it and got T-boned in the intersection.
Okay.
Right?
If we get to a point where interventions are no longer helpful in measuring how well it's doing and figuring out how to retrain the system, we have to rely on these other objective measures. We have to rely on flicker. We have to rely on incorrect probability vectors. Something moved outside of what we anticipated with the probability vector. I like your points about, excessively hard braking, wobbly steering, inconsistent acceleration or braking. These all seem like good things to look at. When we hear Elon saying there's lots of improvements and version 9 is going to be really, really good, do you think that is they've been doing some internal measurements They're measuring things like this and they're seeing better results?
Absolutely. And without any serious doubt, the overwhelming majority of the feedback that they get right now into the system is not human interventions. Like they get a ton of feedback from other things that are not human interventions that help them refine the system. Those metrics they're relevant. They're going to continue to be relevant long after human beings, long after the steering wheel and the pedals are gone. There will still be all these metrics coming back to the car that they'll be using to refine the network. It's a nice talking point to say that interventions are really important, because they are really important. And that's something that you can talk to somebody who drives the car or somebody who's contemplating driving one of these cars around. And they can say, oh yeah, I see this, that if I intervene, it's a thing that goes back to Tesla or goes back to the AP team, and they can use that to refine the software. That's true. But for every human intervention, there's a whole space of other things that the vehicle is taking back. I mean, you were talking about flicker, but that's one example of one category, which is there's probably 1,000 categories, and there are probably dozens or hundreds of examples in each one of those. You probably can't get in your car and drive down the street without generating tons and tons of triggers that go back. Now, Tesla probably gets so much feedback from the fleet that they prioritize.
Yeah.
So like today, right now, we're working on this category of things. We're just going to look at those. They can accumulate this stuff. They can stick it in a database. Maybe someday they'll look at it. Maybe they won't. But they get an enormous amount of feedback from the fleet that doesn't necessarily require drivers to act in some way that's consistent and provides the feedback that you get. Driver feedback is important and it's very useful. And there are some kinds of things that you can get from driver feedback that you cannot easily get from the vehicle, right? But the feedback from the systems in the vehicle itself is just overwhelmingly larger than the human feedback.
Right.
And a lot of the human feedback, I mean, there's, I think, was it Karpathy talked about navigating intersections, right? So navigating intersections is an interesting, it's an interesting edge case in the world, right? Because most intersections are pretty consistent, but you've got some really, really weird intersections out there. And I mean, who hasn't come up to an intersection where you come up to the intersection and the city decided to paint a different number of lanes on one side of the intersection than the other side? You hit the intersection and you have to decide which of those slots your vehicle is going to go into. And sometimes you're off halfway. I mean, just looking straight ahead, you could go to this lane or that lane, and you have to kind of understand, was there a right turn lane, a left turn lane? What are the lights in this thing? I mean, obviously you got to build the intersection so that it's obvious to a human that there's only one solution. You want to build the intersection so that a human being at a glance can tell what lane is the right lane for them to exit the intersection in. But sometimes those are things that you cannot write down, and just like it's hard to write in a short sentence, what's the difference between a dog and a cat? Knowing which lane you need to go into on the other. So a thing that you can do, and the thing that Tesla did do, right, is they started looking at what lane did the human driver take as they exited the thing. And so you train a neural network. Okay, here's the intersection. What lane do you think the human took when they exited the intersection, right? So humans drive lots of intersections, and you capture all these things. Like, here's the intersection. What do you think the human took? Now, occasionally you're going to get a human who changes lanes in the middle of an intersection, and that's going to mess up your algorithm potentially. So you have to have some filters and stuff on that. But you can. This is a simple example of a large space of things where you can train the neural network to just predict what the human driver did, and that can give you an incredibly valuable way of labeling data for a neural network that you just couldn't get otherwise, right? That's a brilliant application, and there's 100 other ones like that too. I drive nav on autopilot pretty much exclusively. I get in the car, I pick my destination, I set nav on autopilot, and I fix it if something goes terribly wrong, but I just see where it goes. So my girlfriend and I, we do tons of long road trips. I've seen every kind of failure that you can imagine. And one that we see a lot these days, because the stop sign recognition has gotten pretty good, is like you're on some rural road and you're coming at some weird angle and there's a stop sign and it's bent, right? A truck has hit it. Or, it's an acute angle intersection and the car's coming up and you can see the stop sign. But the question is the stop sign for you or not? Like, that's actually pretty subtle. It can be hard to tell. And humans make this mistake all the time. They think the stop sign or the yield sign is relevant to them, but it's actually the adjacent road that it's for. So you can do a thing where where you challenge a neural network, like, is that stop sign for me? Right.
Right.
And then you look to see what humans do, because humans are mostly going to get it right. Like if it's a traffic control in the real world that somebody hasn't bothered to fix yet, probably most humans are getting it right most of the time. So you get a good set of labeled data, and you can go on and on. I mean, there's all kinds of things like that. Like, should I drive over the curb here to enter the driveway, or should I, I mean, you can look to see, did humans drive over that curb in that spot or not, right?
Yeah. That was part 2 of my interview with James Douma. If you missed part 1, it's here. Thank you so much for watching. Don't forget the t-shirts, the machine that builds the machine. Check out all the other merch at elonbits.com. Please support this channel on Patreon. Check out the Fair DUI book on Amazon. Links to everything in the description below. Thank you so much for watching.